Hello everyone, welcome to another vectors example using resolution of vectors. So 3 people are pulling on a box using ropes. See the picture below. What is the resultant force of all their efforts? All right, so resultant means the sum, right? So we've got 3 people pulling on ropes, and you can just tell from the picture that they are not helping one another. I mean, you've got people pulling in opposite directions. So the resultant force, I mean, you're not really helping the box move anywhere. So let's figure out what this resultant force is. Now, in the previous video, you would have watched how to solve the sum of vectors using sine and cosine law. But there was a big difference between that question and this one. And that is that the previous question, John only had 2 displacements. In other words, there were only 2 vectors you had to add together to get the third one. In this case, you have 3. Okay, so I'm actually going to label these. So I'm going to call these force 1, and I'm going to call this force 2, and this one here is going to be force 3. You have 3 vectors to add. Remember, force is a vector, and it's measured in newtons, represented by capital N. And I've got their respective angles here. Okay. You're not going to be able to use sine and cosine law. So if you think about it, if you have 2 vectors that you add together, so let's say you have vector A and vector B, kind of like we did in that question, the resultant was from the tail of the first vector to the tip of the final vector. That was the sum. And it can work because then when you have the 2 vectors and the sum, they form a triangle. They have 3 sides. But if you take 3 vectors and you add them together, so if I take, F1 and I add F2 and then I add F3, okay, the resultant, so let me just quickly label this, F1, F2, F3, the resultant is going to be from the tail of the first vector to the tip of the final vector. You are creating a nightmare scenario for yourself in terms of a geometry problem. You can't use sine and cosine law. You're going to have to keep drawing out all these angles. I don't know, it might actually be simple, but I doubt it because this looks very complicated. Solving this kind of a problem, you have to use a different method. Resolution of vectors. If you remember at the end of video 1.3, vectors and scalars, I mentioned something. The word resolve. When the question says to resolve vectors into its components, it means break it into its x and y components. So we're not doing this in this question. That's why this one's called resolution of vectors. So whenever you want to resolve vectors, what I'm going to do is I'm going to try to get it into this kind of a scenario. Okay, so this question is unfortunately a bit longer, but that's just due to the nature of having more than 2 vectors to start with. And resolution of vectors, you can use this strategy when you have 2 vectors to add, 3 vectors, 4 vectors, however many you want. But using sine and cosine law, you can only use it when you have 2 vectors. So for this kind of a question, what I'm going to do is I'm going to draw my Cartesian coordinate system, labeling system rather. So x, y, you always got to draw this if you're going to use the xy coordinate axes. You know what? I'm going to use black to draw the coordinate axes. So draw a large xy plane. Now, what I'm going to do, okay, let me just draw the whole thing. I'll draw all 4 quadrants this time, but you'll see afterward that we don't actually need all 4 quadrants for this question. So x, y. All right. So what I'm going to do now is draw each of these forces along the xy coordinate plane. So I've got 40 newtons at 20 degrees above. That's the longest arrow, so I want to make sure that I draw that one first. I don't want to have to draw them outside of this plane. All right, so 40 newtons. And again, it doesn't need to be to scale. 40, so that's 20 degrees. That looks about right. So let's call that one 40 newtons. I'll fill in the numbers once I'm done for the lengths, once I'm done drawing the arrows in. 15 newtons, and that's 15 degrees from the vertical. So 15 degrees, and that's 15 newtons. So something like that. What else do we have? We have 25 degrees from this line. So a little bit higher than this, and it's 30 newtons. So looking back, the 15 Newton line should probably be a little shorter, but that's not a big deal. 25 degrees. Okay. Make sure your axes are always labeled, okay? Whether you're doing this in physics or math. All right, so let's label the magnitudes now. This is 40 newtons. This one over here, I'm going to label this right here. This is 15 newtons, and this one here is 30 newtons. So remember, to resolve a vector means to break it up into its x and y components. So the easiest way to do that is when you have a vector, so let's say the 40 Newton vector, what I do is I go to its tip and I drop a vertical dashed line to the x-axis. Okay, so I drop a line like this down to the x-axis, and I'm going to do that for each vector. So for the 50 Newton vector, I'm going to drop a line down to the x-axis, and for the 30 Newton vector down to the x-axis. And each of those lines is making a 90-degree angle with the x-axis, whether it's in the positive side or the negative side. All right, and I mean, this is essentially you having created your triangles. If you look, you've got a right angle triangle for each of these now. So for the 40 Newton force, the x component is going right along the x-axis and the y component is going up. So this is, and since I'm doing different colors, I'll keep them solid lines. But if you're using a pencil or just using the same color, make sure you do dashed lines or solid lines. Keep it different. All right, so let's remind ourselves. The 40 Newton force, I labeled that one as F3. So therefore, the y component, this is going to be F3y. And the x component, this is going to be F3x. Labeling is important so that you keep track of everything. Being well organized will help you to be successful in these types of questions. All right, for the 50 Newton force, I'm going to draw its x component underneath because, well, there's not a lot of space. So that's the 50 Newton x component. So this is F2. So therefore, the x component would be F2x. All right, the y component is coming up like this. So that's F2y. And now let's do the last vector there. So that's F1. So we have F1y, and we have F1x. So earlier I said we didn't actually need to draw all four quadrants, and you can see why. Everything's in the positive y here. So I didn't really need to draw the bottom here. But anyways, it's done, so we'll leave it. Now, we've already resolved the vectors into their components. What's important for us to do next is combine all the x vectors and then combine all the y vectors, but keep it separate. Okay, so x vectors, we're going to combine them. Let me just write that here. Combine the x vectors and then combine the y vectors. So the x vectors, it's going to be, we'll call this fx. In fact, you can call it the sum of fx. This letter here, this is the capital letter sigma. It's the Greek letter sigma. So this is a Greek letter, this is capital, right? Lowercase will be something different, capital sigma. It means sum, okay? The sum of all the forces in the x direction is going to be F1x plus F2x plus F3x. Keep in mind that these are vectors, right? So F2x and F3x are both going along the positive x direction, but F1x is going in the negative x direction. So I'm not actually going to be adding these numbers together exactly like that. In fact, when I physically add them, I have to do F2x plus F3x minus F1x, all right? So that's very important. In fact, if you'd like, you can even write the formula like that if it helps you so you don't get confused. But just understand that if you write it as a vector, when you add vectors, it already assumes that you understand that certain vectors have different directions, and those plus and minus lines have to be taken into account. Okay, now we have F1, F2, and F3, but we don't have F1x, F2x, F3x. This is where your knowledge of SOHCAHTOA comes into hand. All right, so let's do F1x first. So notice we've got this right angle triangle here. All right, F1x, this is adjacent to the 25-degree angle, and I have the hypotenuse of 30 degrees. Adjacent and hypotenuse, that's cosine. So cosine of 25 degrees is equal to adjacent, which is F1x, over hypotenuse, which is 30. Right, so remember we did this in lesson 1.3. This is why. F1x is equal to 30 times cosine of 25. I want you to start getting used to seeing it like this. I'm not going to be writing it from this step anymore because this is just, this is already from grade 10. You should already start to see the more you do these problems that whatever side of the triangle you're looking for that's not the hypotenuse, it's always going to equal the hypotenuse times sine or cosine of the angle, depending on whether it's the adjacent or the opposite side that you're looking for. All right, that's important. So notice f1x is the hypotenuse, 30 times cosine of 25 because f1x is adjacent. So grab your calculator and make sure it's in degrees. 30 times cosine of 25, 27.2 newtons. F1x. Now what I like to do is just put certain, I guess, milestone pieces of information in a circle. Don't box it because a box means that's your final answer. Now notice for the x, I'm going to need, well, I used cosine. I'm going to eventually need the y as well when I combine the y vectors. So I'm just going to go ahead and solve that. The more you do these types of physics problems, the more you're going to see that you just have to find these components anyway. So you're just going to automatically start doing it before you even get into the question. The y component, notice that f1y is opposite of 25 degrees. So therefore, f1y is going to equal the hypotenuse, which is 30, times sine 25 degrees. Okay, so this will save you one line. 30 times sine 25. So 12.7, let's call that. So that's f1y. And we got to do this for each of the forces. We got to resolve each of those into their x and y components. There's going to be a lot of information here, which is why I suggest circling your milestone pieces of information. Okay, F2, F2x. Now this one, just be careful because you know the angle that we're using. It's always the angle between the hypotenuse and the horizontal, or in this case, the x-axis. The angle you're given in this question, in this, I guess, setup, is the angle relative to the y-axis. So that's not a big problem. You just have to figure out what this angle in here is. So if this is 15 degrees and the entire angle is 90, 90 minus 15 is 75. So this angle here is 75 degrees. And that's what you're going to use in your formula. So just be careful of that. So F2x is going to be the hypotenuse, which is 15, times cosine of 75 degrees. So 15 times cos 75, and we get 3.88. Let's call that 3.9 newtons. It's pretty small, and as you would expect, you can see it's a pretty small side of the triangle there. All right, so let's find F2y. F2y, that's opposite of angle 75 degrees, so it's going to be the hypotenuse times sine of 75. 14.5 newtons. Okay, nearly there. Let's do it for F3 as well. So F3x is equal to, so F3x, that's going to be the hypotenuse times cosine of 20 degrees. .6 newtons. And now F3y. So that's going to be 40 times sine of 20 degrees. 40 times sine 20. 13.7, let's call that. 13.7 newtons, F3y. Okay, we've got all our components. Now when we plug them into our formula, it makes sense where they came from. All right, so the sum of the forces in the x direction. So we've got x's, right? So F2x, so that's 3.9 newtons, plus F3x, which is 37.6 newtons, minus F1x, which is 27.2 newtons. So let's do this. 3.9 plus 37.6 minus 27.2, that's 14.3 newtons. Now, something important that I should point out, notice that the sign came out positive. The fact that we wrote F1x with a negative sign in front, we did that because it was going left, right? And I defined positive already to be going right. That's why this piece is so important here. All right, so the fact that my resultant came out positive means that my net force in the x direction, my resultant force in the x direction, is going to the right. So just keep that in mind. All right, so we combine vectors in the x direction. Now we're going to combine the y vectors. All right, so the sum of the forces in the y direction. So in the y direction, they're all going in the positive y. So it's just straight up addition. So that's going to be f1y plus f2y plus f3y. So f1y, 12.7 plus 14.5 plus 13.7. That's newtons, newtons, newtons. Okay, 12.7 plus 14.5 plus 13.7, 40.9 newtons. This one I'm not going to round, I'm just going to keep it to 1 decimal place. So sum of the forces in the y direction. All right. This is taking quite a while, and this is generally how it's going to be, especially if you have more than 2 forces. You'll notice, even if you had 2 forces and you did this method, it would take you quite a long time. That's why when you have 2 forces or 2 vectors that you're trying to add, it's easier to use the sine and cosine law method, which is why I showed it to you. If you have 3 or more vectors, you have no choice, you have to use this method. But it's not bad. I mean, we have to use this anyways for our future work. All right. Now we have the sum of the forces in the x, we have the sum of the forces in the y. This is going right, this is going up. We are going to now add these 2 new vectors. Each of these is a new vector now. One going right, one going up. So imagine this thing is going to the right, this thing is much longer and it's going up. We have to add those 2 now. All right. When you add vectors, you add them tip to tail. So I have 40.3 going to the right, or sorry, 14.3 going to the right. And I have 40.9 going up. So just like before, when you add vectors, I know this one's going to the right again because it's x, and this one's y, it's going up. The sum is going to go from the tail of the first vector to the tip of the final vector. So this is my sum. And since these 2 are in the x and y directions respectively, I know that they meet at a 90-degree angle. I have a right angle triangle now. So, yeah, that's what I've got. Now, because it's a right angle triangle, I can find the length of the hypotenuse, which is the resultant total force on the box, by using Pythagorean theorem, right? So if I want to just call that C, I can call these 2 sides A and B, or you can even just call it sum of fx, and sum of fy, like before. And this would just be the sum of the forces in total. Okay, so you can either write it as c squared is equal to a squared plus b squared, or you can be more accurate and you can say the sum of f squared is equal to the sum of fx squared plus the sum of fy squared. Okay, so that's 14.3 squared plus 40.9 squared. Keep in mind that's the square of the total force. Okay, so we have 14.3 squared plus 40.9 squared. What is that? That's 1877.3. And so if we take the square root of that, the sum of f is equal to 43.3. So 43.3 newtons. All right, so makes sense. It's longer than the longest side that is making up the right angle triangle. So there's that. Now we have to find the direction. All right, so the direction is always going to be based on the angle between the resultant and the first vector. So this is my theta that I'm going to find. All right, let's go ahead and do that. So theta, I have opposite, I have adjacent. So I use tangent. Tan of theta is equal to, so sum of f sub y over sum of f sub x, which is equal to 40.9 divided by 14.3. Okay, so actually let's do this. 40.9 divided by 14.3, we have 2.86. So therefore theta is equal to the inverse tangent of 2.86. So inverse tan, theta is equal to 70.7 degrees. It makes sense based on the picture. It's opening up to a larger side. Now, how do we, I think for this, we don't actually have to give it to the vertical because this is not a northeast, southwest compass direction problem, which, by the way, while we're on that topic, I want to point out, since this question did not give compass directions, you cannot invent compass directions and start using them in the question. Whatever direction system the question had in the beginning, you got to use the same direction system. And so this question is just labeling the angles relative to the horizontal and the vertical. So you could use either. Since we calculated the angle relative to the horizontal, we're just going to give our answer relative to the horizontal. So we're going to say that therefore the resultant force of all their efforts is 43.3 newtons. And then in the direction in square brackets, we're going to say at 70.7 degrees above the horizontal. And that's good enough for this question because the direction is not that specifically given in the question anyways. Okay, so there's our final answer. We put that in a box. So just to review the problem quickly, just to go over what we did, there are three different forces, three different vectors acting. Whether it's a force, whether it's a velocity, displacement, you would have gone through the same thing. You just would have represented it with a D or rather an S or a V, depending on what quantity it is. So what you want to do, first, you got to identify your positive X and Y directions. Always indicate that. If it's a question with compass directions, you have to draw a compass indicating which direction north is. Next, draw a large Cartesian coordinate system, label your X and Y axes, draw your forces on, and then resolve them into their individual X and Y pieces. Likewise, you see how I labeled these as F1, F2, and F3? I did that so that I could eventually label my components F1X, F2Y, F3X, etc. That is crucial. You have to have a proper labeling system. Okay? After that, determine what those components are. Calculate them, right? Figure out what F1X, F2X, F3Y, F3X, what they are. Calculate them and show your work. Okay? Once you've done that, combine all the X pieces together, combine all the Y pieces together, and now you have a sum vector in the X and you have a sum vector in the Y. So now you are only adding two vectors. And these two vectors, because one's in the X direction and one's in the Y direction, they will always be perpendicular. Even if this is in the negative direction or this is in the negative direction, they will be perpendicular, which is nice because then when you find your final result, you just have to use Pythagorean theorem and tan of theta. You don't have to go through sine law and cosine law again. That's going to be way too much work. So, right, so we use Pythagorean theorem, find the net force, use tan of theta, find the angle, which is between the resultant and the first angle. Put your final therefore statement in a box. And that is it. So hopefully that is okay. And that is the end of this example. Vectors, resolution of vectors.